Chapter 6 deals with discrete probability distributions, and discrete probability is, you've seen the word discrete before when we talked about different types of quantitative variables, and so we're going to look at what discrete probability distributions look like. And for 6.1, we're going to, again, kind of review on what discrete and continuous variables are. Look at discrete probability distributions, graph the probability distributions, and then look at what the mean, how to compute and interpret the mean and standard deviation of a discrete random variable. First, a random variable is a numerical measure of the outcome from a probability experiment, so the value is determined by chance. Random variables are denoted by using letters such as X. So for example, maybe I said I'm going to flip a coin. I know I use this example a lot, but it's an easy example to use. Whoops. Let's flip a coin 2 times. And I want heads. So X, what could happen basically? If I flip a coin 2 times, I could get 2 tails, which means I get 0 heads. I could get 1 heads and 1 tails, or I could get 2 heads. So those are all the possibilities, and so I'm denoting that random variable with X. Discrete random variables have finite or countable numbers. I think of them as whole numbers, and so maybe it's just 0 or 1 or 2 or 3 or 4, right? It's those whole numbers. So maybe the number of siblings you have, or the number of trees in your backyard. They are whole numbers, counting numbers. Versus continuous random variables have infinitely many values. So it could be anywhere from 0 to 4 and all the values in between, including 1.2467, right? That very specific number. So these are not counting values. I use speed a lot when I'm talking about continuous, because speed can be very, very, very specific. So we're going to distinguish the difference between discrete and continuous, again, just kind of reviewing. A says the number of light bulbs that burn out in a room of 10 light bulbs in the next year. That is discrete because it's, either 1 light bulb burned out or 2 or 3, right? We're not going to have 4.56 light bulbs burn out. It either burnt out or it didn't. The number of leaves on a randomly selected oak tree, that's discrete. I can count the number of leaves. And the length of time between calls to 911 is going to be continuous, because that can be very, very, very specific. I spent 5 minutes, 30 seconds, and 26 milliseconds on the phone with 911. The probability distribution of a discrete random variable X provides the possible values of the random variable and their corresponding probabilities. A probability distribution can form a table, graph, or mathematical formula. So we talked about probability distributions in Chapter 5, and we're going to bring them up again with discrete random variables. So this is what a discrete probability distribution looks like to the right, and it represents the number of movies streamed on Netflix each month per Netflix account. And so X is what you're looking at. It's saying I either watch 0 or 1 or 2 or 3 or 4 or 5 Netflix movies, so they're whole numbers. A lot of people look at this and look at the probability column and say, well, those are decimals. Those don't represent discrete numbers. And so you're actually looking at the X values, and those are the whole numbers that were given. And another way this changes from Chapter 5 is your X is actually discrete, right? We're not talking about color of M&Ms or qualitative data. We're talking about quantitative data now. And another thing that this shows is, I like to talk about it in percentages. It basically says that 6% of Netflix users watch 0 movies, or 58% watch 1 movie. And so that's kind of how you can read this. Couple things you need to know about probability distributions, and they're the same rules as Chapter 5, and there's only 2 of them. Your probability distribution, the probabilities need to add up to 1 whole or 100%, and all the values need to be somewhere between 0 and 1. So I'm going to look, and I want to see if this is a probability distribution. So if you're asked if it's a probability distribution, you want it to add up to 1 and all the values to be between 0 and 1. So first off, all these probability values are between 0 and 1, so we're good there. And if I add it all up, add all these values, 0.16, 0.18, every single one of them, I will get 0.97. Because it doesn't meet both rule requirements, this is not a probability distribution. This one, if I were to add all the values up, I do get 1. So I'm thinking, okay, I'm doing okay, right? But I look down here and there's a negative value. So because of that, it is not a probability distribution either. Lastly, this one, I'm looking at the P of X, add them all up, they equal 1. And they are all between 0 and 1. So yes, this one is a probability distribution. So there's something that exists called a histogram, a probability histogram. And we're going to use this Netflix example again. And all the discrete variables go here. And I'm going to put 0 here, and I know 0 usually goes on an axis, but I'm just going to put it here so you can see it. So 0, 1, 2, 3, 4, 5. So on my horizontal axis is where my random variables go, my x's. And then on my vertical axis is where my probabilities go. So I'm going to try my best. I'm going to count by 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. You could have counted by 0.05s to make it a little more spread out if you wanted to, but that's just an option. And so I'm going to go to 0, and I know the probability is 0.06, which is about halfway to 0.1. And you're going to draw a little dot, and then you're going to draw a line to 0, and it looks like a little antenna. And that's all you do. So for 1, I'm going to go to where 5/8 is, a little under 6. Actually going to line that up a little better. And draw it all the way down to 1. That's almost at 0.6, so sorry about that. 2, I'm going to go to 0.22. Do the same thing. 3.1. 4 is 0.03. And 5 is 0.1. I know 4 and 5 are really close together. Just try your best to try to make some sort of differentiation between them. But that is a probability histogram. The mean of a discrete random variable. So we've talked about means before when we added all the values up and divided by however many there are. You can also find a mean for a probability distribution, and it is given to you with this formula. It's mu sub x equals the sum of x times p of x. X is, again, the random variable, and p of x is the probability. So according to that formula, I need to take the sum of x times p of x. So what I'm going to do is I'm going to create another little column here. And I'm going to multiply x and p of x and then add them all up. So to find these values, I'm going to do 0 times 0.06, 1 times 0.58, 2 times 0.22, 3 times 0.1, 4 times 0.03, which I believe that is 0.12, and 5 times 0.01. So I did the middle part. I multiplied them, but this last part says, the E says to add them all up. So I take each one, 0 plus 0.58, 0.44, 0.30, 0.12, 0.05. I add them all up. I get 1.49. So my mean is 1.49, which basically means that I can expect on average that Netflix users will watch about 1.5 movies per month, I believe this was talking about. So remember how we found mean normally? We added up all the X values and divided by however many there are. The process is still the same, except now we're given a probability distribution. And so on the next slide, I'm going to show you why this would end up being the same answer. So let's say I had 100 Netflix customers before I put it into a probability distribution. So since that 0 was 0.06, that basically meant that 6 zeros existed, or 58 ones existed, because 58%. And so if I were to add all these values up and divide by 100, I would still get that 1.49 that I got before. And so all this is proving is that it still works. It's still legit. You're still getting basically the same information. There's just a different way of doing it. And this basically just says, and we've kind of brought up law of large numbers before, but the more you do your data, the more trials you conduct and the more samples you obtain, the closer you'll get to what you're actually trying to look at. So if I just asked 2 people how many movies they watched on Netflix and they both said 5, that's not enough evidence for me to say, well, I guess everyone watches 5. I need to ask more people to get the true idea of how many movies people watch a month on Netflix. Anytime you see the word mean and expected value, they mean the exact same thing. It wants to know what's going to happen in the long run. So if you see expected value, it is that exact same formula. The sum of x times p of x. Add them all up. So take this example. A term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose a life insurance company sells a $250,000 one-year life term insurance policy to a 49-year-old female for $530. According to the National Vital Statistics Report, the probability that the female will survive the year is 0.99719. Compute the expected value of this policy to the insurance company. So we want to know, what does the insurance company expect to make? And when we do expected value, that's still that formula. So we need to find x times p of x. So let's talk about this table really quick. So they get $530 if she survives, right? She's paying the insurance company $530. And the probability that she'll survive is that 0.99791. If she dies, let's assume she already paid the $530 amount, then the insurance company has to pay $250. And so once we subtract that from the $530 she's already paid, they're out of pocket $249,470. The probability that that would happen is that 0.00209. I got that from doing 1 minus 0.99791. Because if the probability she lives is at 0.99, then to find the opposite, the other, we have to subtract that from 1. So to find the expected value, once you've created this table, I need to, sorry, that's my dog. I need to create another table. So I'm going to do 530 times 0.99791. and I get 528. I'm just going to go to 2 decimal places, but it's 0.8923. Then I'm going to do that $249,470 times 0.00209. And I get negative 521.3923. I'm going to subtract those from each other. Really, I'm adding them, but since one's negative, it's 528 minus that 521. And I need to do this really quick. 528 minus 521.39. And I get $7.50. So it's positive, which means that the insurance company expects to make $7.50 off of this female for the year. If it was negative, they wouldn't be doing a very good job. Their business would go under because they're not making any money. You can also find standard deviation if you're given a probability model. And I use the second one. And do notice that that second value is just the mean. So we're going to do the sum of x squared times p of x minus the mean squared. You can rewrite that mean squared like this. It's literally the mean squared. So it looks a little different there, but it's still the same thing as squaring it or multiplying it by itself. So we want to compute the variance and standard deviation. And in order to do that, I need to find my x squared. So I'm going to create another little table here. So my x squared, so 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And I'm going to write this formula up here. It's the square root of the sum of x squared times p of x minus mean squared. And we've already done the mean, and it was 1.49. So all I need to do now is multiply x squared times p of x and add them up. So I'm going to go ahead and do that. I don't even need my x's anymore, so I'm just going to ignore those. And I'm going to do that right here. I'll do it right here. Sorry, I'm being indecisive. I'll do it right here. Okay, so I'm taking x squared times p of x. So this times this, 0. 0 times 0.06, right? That's 0. Then I take 1 times 0.58, that's 0.58. 4 times 0.22, 0.88. 9 times 0.9, 9 times 0.1 is 0.9. 16 times 0.03 is 0.48. 25.05 is 0.25. Add all of those values up. 0, 0.58, 0.88, 0.9, 0.48, 0.25. You should get 3.09. That we just got is all of that. We multiplied them together and we added them all up. So 3.09 minus that last part, that mean, we have that right here. So minus 1.49 squared. All that's under your square root. And I'm going to do this really quick before I square rooted it. I square rooted it already in my notes. So if you do that, you should get the square root of 0.8699. This number, before you square root it, this is actually your variance. So my variance is 0.8699. I'll write that in a second. And then when I end up square rooting it, I get 0.9327. I'm going to go ahead and erase this in a second to write my final answer. So be ready for that. So my standard deviation was 0.9327. And then your variance is always that number right before you square root it. I believe, I didn't write it down, I'm sorry. I think it was 8966. 8699, sorry. And that just went away. So that 0.8699 was equal to my variance squared. My variance was just my standard deviation squared. And then right after I square root it, that 0.9327, that is your standard deviation. (6.2) talks about binomial probability distributions. So the first thing we need to learn is how to even figure out if it is a binomial experiment. Compute the probabilities of binomial experiments. Then find the mean and standard deviation of a binomial experiment. So you've basically got a couple things that you have to meet, a couple expectations if you want it to be what you're doing, a binomial experiment. One is you have to say that it's performed so many times, a fixed number of trials. So I can't just say I want to ask people if they got an A on this test until I find 10 people. No, I have to say I'm going to ask 20 people and see how many out of those. The trials have to be independent, so remember that means that one outcome won't affect another. They have to be mutually exclusive. So Texas Tech baseball player, UT baseball player, right? You can't be both is what mutually exclusive means. And the probability of success is fixed for each trial of the experiment. So there's some notation that we can look at. N dictates how many trials. P deals with the probability of success. And so if you want to find the probability of failure, that's 1 minus P. X is the binomial random variable, and so it needs to be somewhere between 0 and N. Here's a couple examples that we're going to look at to see if they are binomial experiments or not. A says a player rolls a pair of fair dice 10 times. The number X of sevens rolled is recorded. So we have a fixed number of trials. So N is equal to 10. It is independent because what I roll on one roll won't affect what I roll on the next roll. The success is constant because I each time I roll the dice, I have the same probability of rolling a 7 as I did previously. And it is also mutually exclusive because you either get a 7 or you don't. It's either or. So this one is a binomial experiment. B is the 11 largest airlines had an on-time percentage of 84.7%, so that's a fixed success rate, according to the Air Travel Consumer Report. In order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that need to be selected is recorded. This one is not, because she's just waiting until she finds what she wants to find. She doesn't have a fixed number of trials. So if it doesn't meet one of those 4 rules, then it doesn't meet it. And then C says, in a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number of females selected is recorded. So this is not, because it's not a fixed success. Let's say I take one student at the front of the room, and so if I select one girl, that affects the probability of another girl getting selected. So these are dependent, not independent trials. According to the Air Travel Consumer Report, the 11 largest air carriers had an on-time percentage of 79% in May 2008. Suppose that 4 flights are randomly selected from May 2008, and the number of on-time flights X is recorded. This wants us to create a probability distribution. I'm not going to do that because I'm going to do it a little later with something else. But what we can do is we can find P, which is the probability of success. So in this case, the probability of success is on-time percentage, which means the probability of failure is 1 minus P, that they're not on time, so 0.21. Okay, so this is a very long, fun formula. This is how you calculate a binomial probability distribution. And so you're going to be using this. And I like to break it up. So P of X is NCX times P to the X times 1 minus P to the N minus X. So basically, you can use the formula that we learned in Chapter 5 to find NCX. That's the number of possible combinations that something can have. Or you can do it in your calculator. And then this is just the probability of success. And then this one's just the probability of failure. So you're basically taking all things into consideration when you calculate binomial probability. This says, according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. So that 35 is your P. So your 1 minus P is 0.65. A says a random sample of 20 car-owning households, what's the probability? Exactly 5 have 3 or more cars. So your N is 20 because you're looking at 20 households. And we're going to use that formula. So you might want to write it down because I don't have enough room to do it on this sheet of paper or on this slide. I'm just going to have to go straight into it. So it's going to be 20C. And it wants to know, well, what is X? What are we looking at? In this case, X is 5. So 20C5 times P to the X, so 0.35 to, we want exactly 5, times 1 minus P, which is 0.65, to the N minus 5, which is 20 minus 5. When I do that, I'm going to go ahead and put the numbers that I get for each of these so you can kind of follow along in your calculator and make sure you're doing it the right way. So when I get 20C5 in my calculator, I get 15,504 times 0.35 to the 5 is 0.00525 times 0.65 to the 20 minus 5, or to the 15, is 0.00156. Multiply all those together, I get 0.1272. I'm still on A, but I'm just taking up a little more room. So A, the answer is the probability that X is exactly 5 is 0.1272. Okay. So we're basically plugging it into that formula every time, and I'm going to have to erase this because the next one's really long. Okay, still same information, except N is still 20, P is still 0.35, and 1 minus P is still 0.65. Sorry. B says in a random sample of 20 car-owning households, what is the probability that less than 4 have 3 or more cars? So less than 4 includes 0, 1, 2, 3, 4. No, not 4. Less than 4 only includes 0, 1, 2, 3. Sorry. So we're basically going to have to do what we just did 4 times. It could be or 0, or 1, or 2, or 3. Remember, or in math means to add. So if we want to find less than 4, we have to do that 4 times basically and add them all together from 0 to 3. So to find the probability that x is less than 4, that's the same as the probability that x is 0, plus x is 1, plus x is 2, plus x is 3. Sorry, I'm running out of room. And I'm probably going to have to erase this quite a lot just because of how much work it is. Not how much work, but how much writing it is. Okay. So I'm going to do it for 0. And then I'm probably just going to give you the values. Well, I'll do it for 0 and 1. And then I'll give you the values for the rest. So I'll try to fit as much as I can. So for 0, it would be 20C0 times 0.35 to the 0 times 0.65 to the 20 minus 0, which is just 20. Plus 1 would be 20C1 times 0.35 to the 1 times 0.65 to the 20 minus 1, which is just 19. I'm going to do the 2 and 3 down here, actually. The next one, 20, is just, 2 is just 20C2, 0.35 to 0.65. 20 minus 2 is 18. And then lastly, 3 is 20C3, 0.35 to the 3, 0.65 to the 20 minus 3, which is 17. Notice that the only thing that's changing is the x. Here, x was 0, 1, 2, right? I'm going to go ahead and put what I got for each one. So for 0, if you plug in the 0 in your calculator, that whole thing, you should end up getting 0.00018. Plus, if you were to do the 1, 20C1, all that, you'd get 0.00195. Plus, if I plug in the whole one with the 2, it's 0.00998. Plus, the one with the 3 is 0.03226. So if I add up all these together, that's the probability that I get that less than 4 car-owning houses have 3 or more cars. All right, I'm going to go ahead and erase this soon. Well, I'll just go ahead and tell you. When I add all those up, I get 0.044444. So that's the probability I get an x less than 4. So that's your answer to B. And C says, I'm just going to kind of leave this up here for another second. C says, in a random sample of 20 car-owning households, what's the probability at least 4 have 3 or more cars? So at least 4. At least is tricky. At least 4 would be 4 or 5 or 6 or 7 all the way to 20. And we just found out that 0 to 3 was that 0.0444. If we know 0 to 3 is 0.0444, then we can find the other. We can find the leftover, basically, We don't have to do that whole thing again, the probability of 4 plus 5 plus 6 plus 7 all the way to 20. That would be really long. So the probability that we find a house of at least 4 is equal to 1 minus that 0.0444. When I do that, I get 0.9556. That is a couple different examples of how we can find the binomial probability using the distribution, using that function. Just like when we have a distribution model, we can find the mean and standard deviation. I think this formula is a little easier, even so, versus when you have a table. To find mean, you just do n times p. And to find the standard deviation, you just do the square root of n times p times 1 minus p. All you need to do here is to find n and p, basically, and you've got everything you need for this formula. According to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and standard deviation number of car-owning households that will have 3 or more cars. So first, we need to identify what your n is and your p. Your n is always how many trials or samples that you're looking at, so in this case 400. And your p is that proportion that you're given of success, so 0.35. If you want to find mean and standard deviation, we're going to use the formulas that we were just given. So to find mean, it's n times p. Whenever you do these in your calculator, you need to turn them into a decimal if you're given them as a percentage. And when we do this, we get 140. So on average, I could expect to find 140 households that have 3 or more cars. Standard deviation was the square root of n times p times 1 minus p. So 400 times 0.35 times 1 minus 0.35 or 0.65. If you forget to square root, you will just get 91. Don't forget to take the square root at the end, so you get 9.54. Just like anything else that we've done in this class, we could look at it on a histogram and comment on the shape. And so this says we have a trial size of 8, probability of 0.15. If I draw a little shape above it, it looks like my right foot. So this is skewed right. That one where it's perfectly symmetrical or pretty close, that is bell-shaped. And then this one kind of looks like my left foot. So this is left skewed. Now, if I look at this one, even though it's physically to the right of this table, just kind of ignore this. The graph itself kind of looks symmetric, although it's got a little tail over here. And this is with a sample size of 25 and a probability of 0.8. Now, if I do it again, but I have a bigger trial size, I'm getting a little more even, right? A little more symmetrical. And lastly, if I do it with 70, it's almost perfectly bell-shaped. And really, the rule of thumb here is the bigger the sample size, the better. It will normalize your data, and it's when your data is normalized, you can basically say it's legit. It is probably annoying to try to have to make a histogram for every time that you have data. And so there is a rule that we can use. And if it passes this rule, then we can say it's pretty much normal. It's pretty much bell-shaped. I don't have to create a histogram every time. And that rule is n times p times 1 minus p needs to be greater than or equal to 10. This basically ensures that you did enough samples to have legit data. Lastly, I don't know if you remember the empirical rule, but it was basically when we had a bell-shaped distribution, the mean's in the middle, 68% of our data lies within 1 standard deviation of the mean, and 95% of our data lies within 2 standard deviations of the mean. And so if we find something that lies within 2 standard deviations of the mean, we can say it's pretty normal because that's 95%. But outside of 90%, there lies 5% out here, right? In these two tails. The leftover. And anything outside of that 95%, that 5%, we can say is unusual because it occurs less than 5% of the time. And so in order to figure out if a value lies within or outside that 95%, you can do mu minus 2 times sigma, which would give you this value here, and then mu plus 2 sigma, which would give you that value here. So it's basically creating those lines for you to see where the usual values are and where the unusual values lie as well. So last example, according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. A researcher believes that this percentage is higher than the percentage reported by Experian Automotive. He conducts a simple random sample of 400 car-owning households and found that 162 had 3 or more cars. Is this unusual? Well, before we can use the empirical rule, we have to figure out if this data is normal. And so we're going to use this rule. N times p times 1 minus p needs to be greater than or equal to 10. My n is still 400. My p is 0.35. So I'm going to go ahead and plug in this information. This is basically your standard deviation before you square root it. So it's your variance formula. But anyways, that 91 is greater than or equal to 10. So this basically tells me that my data is normal and I'm good to use the empirical rule. So I'm going to go ahead and do that, but I'm going to go ahead and erase this really quick. So remember from earlier that my mean was 140. This is the same information. And my standard deviation was 9.54. So we're going to use that formula that I showed you on the previous page. Mean plus or minus 2 sigma, basically. So I'm going to do the plus one first. 140 plus 2 times sigma, which is 159.1. And then mean minus 2 sigma, which is 120.92. So I basically have these fences. And I want to know if 162 is unusual. And so if it lies within these fences, it's not. And if it lies without it, it is, because it's part of that outside 5%. So 162 is a little past 159. So is this result unusual? Yes. Let's say I did an example where I asked you if 121 was unusual. Well, I know 121 is barely in there, but it's still in there, so 121 would not be unusual.